So let's start recording. So this is the next section in chapter 16 that we're going to talk about. But tomorrow we're going to have the midterm 3, right, covering chapter 9, 10, 11, 15, right? So you have, remind me what chapter 9 was about? Linear momentum, right? Chapter 10 was on, sorry. Wait, no, what's chapter 9 about? Listen, I'm sorry? Linear momentum, okay. And then chapter 10 was on what? That's the first rotational motion chapter, right? How do things rotate around? And then 11, it's on rotational momentum, okay? And then 15 is the oscillation chapter, right? This, which was just finished. Okay, and then now 16 is not gonna be on the midterm. It's gonna be on the final, of course. And this is going to be on waves, and we're kind of smack in the middle of it. And I've been going through this chapter slowly, so we're not covering too much material before the Thanksgiving break. But let's review what we, actually, before we say that, right? So, but hopefully by the end of class today, we're going to be able to calculate speeds of waves, okay? But when I say that, I don't mean, you know, oh, if you know the wavelength, you know the frequency, you can actually always calculate the speed of the wave. But like, let's say I have a string attached to a wall, right? How fast is that actually that speed without knowing the wavelength or without knowing the frequency? So this is sort of a more physical aspects of these waves, and we can actually, these will have different ways to calculating them depending on what type of waves we're talking about. So we're kind of deviating from the, you know, all the waves behave the same way, but then we're going to have to calculate each types of wave differently, okay? Just to remind you, right, to describe a wave, right, is this sine function where you have some amplitude, and then you have this thing k, with this weird k, right, which is like 2 pi divided by the wavelength, right, which is actually known as the wave number, okay? And then omega is the angular velocity, okay, right? And if you want to convert all these, you know, for example, convert to periods, is 2 pi over the omega. And then the frequency is 1 over the period. There's all these formulas, right? And the wavelength is actually 2 pi over k. There's all these formulas around. All these will be given to you, but you kind of have to know how to use it, right? Because otherwise, you won't be able to convert one to the other, okay? And last time we talked about this idea called the wave equation, right? Whereas this complicated second order differential equation, but we're not trying to solve that equation because we're actually already given the solution. The solution is up here, right? We don't have to solve it, but there are properties that are interesting on here, right? Where this factor in front here, we're going to see that how this is going to be allow us to calculate the wave speed for any type of wave, because it has this factor of 1 over the speed square here, okay? And we're going to try to figure out how that would be, how to figure out what that speed is without, you know, knowing the wavelengths or the frequency, okay? And yesterday we get to, you know, practice graphing some waves, right? And as I stated before, typically on a piece of paper, you would actually plot maybe, you know, y as a function of x for some constant t, right? Yesterday we just set t equal to 0, but t could be equal to 10, 20, 50, just some constant, right? The other way to look at a wave is actually the position, you know, the y versus t, right? How high it is versus time instead. But in that case, you have to set x to be a constant, right? Because this wave equation, this wave solution has 2 variables in it, right? It depends on x and time, okay? And so on a piece of paper, you typically just plot one, but on the computer, you can actually see both at the same time. It gets a little bit hard to interpret. So this is actually a website called GeoGebra. Okay, so actually it's like either a geography place or a geology. I'm not sure which geo they're talking about. But this little complicated plot here, just to note what the axes are. So the red axis is like x. The green axis is time, right? And the blue axis going up and down is the y, you know, oscillating up and down, okay? And it's really hard to interpret this numerically, like 1 point at a time. But you can see that these are little waves that's kind of rippling around, right? So you can see that the wave behavior of this. The way you can interpret this is kind of going back to how we do it on paper, right? So let's say, right, if we set t equal to 0, if t equal to 0, that's this green axis here, right? If that has to be 0, we're only following the wave along this direction, okay? And as you can see, it is a sine wave, right? But if you set x equal to 0, what happened is that then you're actually following only along this green axis, okay? And then along this green axis, you have a sine wave also. So that's the idea of what we did yesterday, okay? Hopefully you guys can, it's hard to see in this three-dimensional view, okay? But just to know that the amplitude of the wave depends on both the time and the position, okay? And that's what this looks like in a three-dimensional plot, okay? Today, we're gonna try to figure out how to calculate speed of waves if, we don't know what the wavelength and the frequencies are. Specifically, we're gonna try to calculate the wave speed on a string, okay? For example, if you have, okay, someone who knows music have to help me. I know this one is the violin. The smaller one is like the viola, or is that the bigger one? Anyone knows? I know this, what's the biggest one? Cello, right? Yeah. Okay. Well, I know this one on the below. Okay, that's the guitar. Okay, at least I know that one. Okay. So on the guitar, you have strings, right? Okay, that are tied to both ends, on both ends with some tension. When you pluck the guitar, it produces certain waves, specifically sound waves. That's actually what you hear coming out of the guitar. Okay, what we're going to try to do is actually try to figure out how do we calculate how fast these waves along this guitar string is traveling back and forth. Okay, so you can figure that out. Okay, so we go away from the guitar, and now we're only zooming in to like a little string. Okay, we're going to zoom in all the way to one particular guitar string. Okay, and this is the string, and we'll just kind of zoom into it. Okay, so on the guitar string, right, you're going to have some forces, notably the tension that's pulling on both sides to the left and the right. That way it's, tight, right? Okay. On each little tiny segment, delta X of a guitar string, right? You have a certain amount of mass. To calculate that mass, you take that little segment, that width, and you multiply by this thing called mu, where mu, right, is the mass density of the guitar string, okay? How many kilograms does it weigh per meter, okay? So this is saying how many kilogram per meter does it have, okay? So that's actually the units for it, okay? So in the little equation, this will be the mass of the string divided by the length of the string, okay? Okay, right? So that's just a definition of this mass density thing, okay? But when you pluck at the guitar string, right, it's not going to stay flat like this. It's going to actually have waves that's going up and down on it. And let's see how those are going to look, okay? So when you pluck a guitar string, okay, there's going to be some vertical displacement of the guitar string versus position, right? And then if we look at this little guitar string, just, the blue is the string itself, right? There's going to be forces that's acting on it, okay? That's A, if it's up here, it's going to be trying to pull it back down, right? But then when it's down here, it's going to try to pull it back up. So it's kind of wobbling back and forth like this, okay? So these force vector, if we draw this, right? There's going to be some vector, some piece of it that's pulling it to the left and right, just like up here, right? Where you have guitar, you have tension pulling it to the left and right. There's also going to be some force that's going to be pulling it up and down, right? We're going to call that force 1 at position x1, and then force 2 at position x2, okay? We're just declaring a bunch of variables, okay, for now. Okay, so what's interesting is that while the net, if you just take a look at this little tiny segment of the string, right? The net force on this is actually force 2 plus the tension force, right? Okay. And then if you look at this tiny segment here, it's force 1 plus force of the tension added vectorially, right? That's how we deal with forces. One thing to note is that the tension force is equal on both sides, right? That's why I don't have a tension force 1 and tension force 2 because there's equal tension along the entire string, right? Okay. All right. So how is this helpful by declaring a bunch of mathematical gobbledygook that we're not sure how to use yet? Okay. So I'm going to zoom out a little bit so we can see this string at the same time as the equation. Okay. So what we're going to do is we're going to do some, sorry. Did I just delete something? Yeah, I think I just deleted the string. See if I can do a Control Z here, like this. Okay, I'm going to do, okay, move this up a little bit. Okay, I'm going to look at the ratio between F1 over the tension force. Why am I doing that? Okay, the ratio of this over the tension force, this is, well, it's the drop, but it's like the rise, right? This is kind of like the rise. And the tension force is going horizontal. That's kind of like the run. When you have a rise over one run, you get what from a graph? Slope. Yeah, exactly. Okay. So as you learn from calculus, right, the slope here, right, that can be calculated also by computing the derivative with respect to x, right? Because we have a function of y versus x. So instead of x versus time, right, you have to compute the derivative with respect to x instead, okay? Because you have a function of x instead, okay? The reason for this negative sign is that you can see that all of this is up, this is the drop over the whatever opposite of run, backward run, right? That's why there's a negative sign here, because all of this is actually backward, right? So that's the slope. This ratio here calculates this direction where the slope we actually want is in the positive direction, right? Right. Similarly, right, the ratio of F2 over the tension also gives you the slope, but gives you the slope at different points, right? The slope is like this here, the slope is like this here, right? They look the same, but you know, if we take this point and this point, they will have very different slope, right? Okay. So we have to actually account for that. Okay. So how is that useful? What we're going to do is, since we care about the motion in the y direction, meaning how fast is it wiggling up and down, right? The net force, if you put y direction, is actually force 1 plus force 2, right? On that particular segment. Since the tension force is equal between them, okay? So what we can do is actually solve for force 1 here, which is going to be equal to negative. These little squiggly sign is just think of them as derivatives. I'm even going to write them as just total derivatives, okay? If you don't know what the difference is, it's not that important, okay? Times force t, and then force 2 is equal to negative dy by dx, okay? And then force of the tension, okay? Right? So I'm going to kind of ignore this little sign here because I know that force 2 is going to pull the string up. Force 1 is going to pull the string down, right? So they actually act in opposite direction. So when I add these two forces together, force 2 is going to be positive, and then force 1 is going to be negative, okay? All right. All right. Dr. 2 is going off on his little math tangent, you know, craziness again. Okay. But the cool thing about this is that, well, if you have the net force on something, that always tells you the mass and the acceleration of that something, right? Okay. The mass here, right, is just a little segment, delta m, right? I probably should have just wrote delta m up here, okay? the acceleration, of course, right? Acceleration is always going to be whatever that variable is, the second derivative, right? Remember you have position, right? If you take the first derivative, you get the velocity. You get the second derivative, you get the acceleration, right? So all of this mathiness gets kind of complicated, but right, this delta m actually turns out to be a little the mass density times the little bit of segment. This is where we zoomed into the little stuff up here, right? That's the little mass here is actually whatever the density is, which is uniform across that guitar string, times the length of that little segments we're talking about. Okay, so this little segment here is delta x, right? All right, okay. A little bit more algebra, then we'll get to the point. Sorry about that. Okay, if I take this delta x divided by both sides, okay, what happened is that then I have some first derivative subtracted to each other divided by delta x, okay? And this may have been forgotten when you did your calculus stuff, okay? What happened is that when you take the limit as delta x goes to 0 there, right, it basically increases the order of that derivative. Instead of a first derivative, it makes it a second order derivative, okay? Okay. So, okay, just like if you have y2 minus y1 divided by delta, not delta t, delta x, right? And you take the limit as x goes to 0. This turns it into the first derivative with respect to y. If you have the derivative of y, right, already, this is that 1, well, 2 and 1, right? And then you divide that by delta x, it basically just adds another derivative, okay? Not add, but like it makes it a second derivative instead of a first derivative. Hopefully that logic makes sense at least, even though if you don't remember it from calculus class. Okay, so that's sort of what we want to get to, right? The right-hand side here, right, is this second time derivative, right? But then there's this factor of mu, and this tension force was brought over to the right as the denominator, okay? So what happened is that this equation turns out to be, well, you have second derivative with respect to x, okay? And then second derivative with respect to time, and then some weird factors in front that we don't know about yet, okay? Well, we know what it is. It's the mass density and the tension force, okay? So what we're going to do is going to go back to section 16.2 and compare it to the wave equation that we found in section 16.2, right? All you have to do is think about, well, you have a second derivative on the left here. You have a second derivative on the right here with time and x's, right? This stuff in the middle has to be corresponding to each other, right? So mu over ft has to be 1 over v squared, right? So this is how we can find the speed of a wave on a string, okay? Because if you solve this for the speed, right, the speed of the wave on a string is just the tension force on that string, right, divided by the mass density of that string, all square rooted. Sorry, that's very important actually. All right, I'm gonna give you guys one more little thing here, okay? The tension force, right, is basically how much tension you are applying to your string as you stretch it, right? Okay, this is known as the elastic property of the string, how much stretching, how much, when you stretch this thing, right? Here, someone wants to, Anthony, you want to try, right? If I don't stretch it that much, if you pull it up and down, right? It's not that hard, right, to do that, right? If I stretch it a lot and you try to pull it up and down, it's harder now, right, for you to stretch it. So the more tension you put on it, the more elastic force it has, okay? Right? This mu thing is the mass density, right? How much mass is there per meter? This is known as the inertia property, meaning, you know, the more mass something is, the less likely it'll move. So if I, you know, going back to chapter 5, right? If I push a basketball, it will go pretty fast. But if I do the same thing with the truck, it's not going to move that much, right? because the truck has a lot more mass than a basketball. Okay, this is going to come into play when we talk about how we can actually generalize how to figure out the speed of any waves. Okay, so this is particularly for string. Okay, this is for any waves. Okay, which is very important and useful to kind of at least get the understanding of. Okay, so let's do a quick example where we're using this equation that we just found. So we have a guitar string. With the guitar, there's actually two E strings. There's a low E string and a high E string. Anyone play a guitar knows this? I didn't know this until I read this in the book a couple of years ago. Okay, Jacob here, you know about the high E versus low E. You can instantly tell that the low E is a thicker string, right? So therefore, it has a higher mass density. Okay, the low E has a thinner string, so it actually has a lower mass density. Okay, so in this problem, the high E string has this mass. So let's just get our information gathering done, right? Right, high E, right, is 3.09 times 10 to the negative 4 kilograms per meter, where the mass density of the low E string is less, no, low as in not low in mass, low as in low in the sound that it makes. Has actually a bigger mass density, kilogram per meter, okay? If the high E string is plucked, so we actually want this one, okay? And what is the speed of the wave if the tension on the string is 56.4 newtons, okay? So that's actually the tension, 56.40 Newton, okay? So to find the answer, well, you can write the CC also, but we're just gonna use this equation here, where the speed of the wave, right, is the tension divided by the mass density, right? In this case, we're gonna use the mass density for the high E string because that's what part A asks us to do. Okay, we calculate that. 56.4 divided by 3.09, 10 to the negative 4, right? All square rooted. The speed of the wave on the string is going to be 427 meters per second. Okay. All right. So I'm going to also do part B real quick, if I can zoom out a little bit. Right. Part B is kind of like a weird wording. Okay. The linear density of the low E is about 20 times greater. I mean, we kind of know what that is, right? Just because they gave us those numbers. For waves to travel through the low E string with the same speed as the high E, what does the tension have to be? Okay, so in this case, right, they want you to find the new tension if the speed is the same, right? Which is this one, right? So in this case, they give you the speed, but they want you to solve for the tension. So that requires a little bit of algebra, right? So you have to square both sides, okay, to get rid of the square root. So V squared is equal to the tension divided by mu. And then so V squared times mu is actually the tension, okay? And this mu is the low E string, okay? The low E one, okay? So if I square my speed multiplied by the mass density of the low E string, which is this one, 5.78 times 10 to the negative 3, okay? The tension, did I do that right? Yeah. That seems like a lot of tension. Okay, 1,500 Newton. Is that right? Yeah, actually, yeah, that makes sense. Sorry. Okay. So you have to string your low E string, extremely high tension, which is actually going to break the string. So typically you actually, so the different string actually gives you different speed, okay? All right. So that's how you deal with the speed on a string equations, okay? And as I mentioned, right, that's actually only for particularly for string speed on the string. But this actually generalizes to other waves also. For example, if you want to figure out the speed of waves in a fluid, okay, you also want to think about what is the elastic property of a fluid and then inertia property of fluid. I know these are like weird words that we don't typically use, but to find the speed of waves in a fluid, right? There's this thing called bulk modulus. Okay, don't worry about what that exactly means because we kind of skipped the fluid mechanics chapter, but these will be given to you. The units for them will be in gigapascal. Okay, so Pascal is the SI unit. So when you do gigapascal, you actually have to take 10 to the 9 Pascal. Okay, okay. So this is the SI unit. Okay. Okay. So when it has a G in front, make sure you multiply that number by 1 billion. Okay. And then on the bottom here is actually the density of that particular fluid. Okay. So this is known as the bulk modulus. These are just weird words. Okay. But these are variables that are given to you. Okay. I'm just going to do a couple of examples. So this table gives you a bunch of bulk modulus. And if you look up the density, you'll be able to actually calculate the speed of waves in these particular fluids, okay? So an easy example is air, right? We kind of already know what the speed of sound in air is, okay? There's actually 2 bulk modulus for air. We're going to use the 142 because the isotherm is actually a special case where you have a constant temperature, which actually doesn't happen when you're making sound in the air, okay? And the other one is known as adiabatic. Does anyone heard of this word adiabatic expansion? Probably not the computer science people, maybe the chemistry people. Okay, all right. But that's what happens when you make sound. You have these adiabatic expansions. Okay, so the speed of the wave, right, is this weird bulk modulus variable divided by the density. The density of air is about 1.25 kilogram per cubic meter. So this is all in SI units. Okay, kilopascal, right? That's going to be 142 times 10 to the 3 because it's in kilo, right? And this will be in Pascal. And then the density down here is 1.25 kilogram per cubic meter. So this is an SI unit. This is an SI unit. So you can count on it kind of being able to cancel each other out so that whatever your answer is going to be in meters per second because meters per second is the SI units, right? So 142 times 10 to the 3 divided by 1.25 kilograms, all square rooted. You get the speed of sound in air to be about 337 meters per second, which is actually approximately what they are at sea level. That makes sense? Okay, so if you know the bulk modulus and you know the density of that material, you can always calculate the speed of sound in those material. Sorry, the speed of compression waves in those material, okay? And this is actually, if Ethan, you want to start passing out the worksheet, this is actually how geologists use sound, compression waves, or known as a seismic wave, to determine what type of materials below ground without digging a big hole to look at it, okay? What happens is that if you emit a sound, this is the source of the sound. What happens is that the sound is going to bounce back to the bottom, at some thick layer down here, right? But the speed it comes back, is determined by what type of material is in here. So if this layer is like granite and this layer is shale, the sound is actually the compression wave will travel faster in granite and slower in shale. Okay, and that's what we're going to see in the worksheet today. So this way you can actually map what's underground without actually digging a big hole to look at it.